Okay, we're now into section 2.5. Section 2.5 is about continuity, and throughout your mathematical careers, you're probably very comfortable with continuity in the sense of we always kind of talked about it in algebra as if you could draw the function without lifting up your pencil and putting it somewhere else, then we have a continuous function. And that idea still extends into calculus, except we do come down with a much more rigorous definition of continuity. Continuity at a certain point at x equals c is defined now as the limit of f of x as x approaches that c. Not only does that limit exist, but it actually has to be the function value at that c. In other words, as x is approaching c and the function looks like it's getting closer and closer to a certain point, a certain y value, it actually has to be that y value for it to be continuous. And if we're talking about the endpoint of a certain region, then either if I have a left endpoint, the limit as x approaches that left endpoint from the right has to be the function value, and the limit as x approaches a right endpoint from the left has to be that function end value. So interior points is the most important point to understand here. So that's essentially continuity real quick. Please make sure you read through everything else. To actually test for continuity, then we have three things we have to check now, right? You have to make sure that the function value at the point we're interested in exists. The limit as x approaches c of that function exists and actually has to be that function value f of c. And these are just some pictures of some functions that are continuous or not continuous. This one's continuous everywhere. This one's not continuous at x equals 0 because there's a hole here at x equals 1. This one also has a hole at 1, but it's a removable discontinuity because it's just moved up to here. Okay, this is called a jump discontinuity, where we just jump to a certain value at a certain y value at a certain value of x. So that's a jump up. This is called an infinite discontinuity, where on both sides of 0 the function looks like it's shooting up to infinity. That's the famous 1 over x squared. We certainly know that 1 over 0 doesn't exist, so this function doesn't exist at 1 over 0. But as x is getting closer and closer to 0, this function shoots up and is getting closer and closer to infinity. That's an infinite discontinuity. This is what's called an oscillating discontinuity. It oscillates so fast in here that you really can't see where it is at any point as x gets close to 0. So that's a famous function called the sine of 1 over x. Okay, properties, continuous functions, sums, differences, etc. If a function f and g are both continuous at x equals c, then all of these different evaluations of a property of functions, whether I add those two functions or subtract those two functions or multiply one by a constant, etc. The only place you have to worry about, of course, is if you're dividing by 0. So you can't ever divide by 0. And again, I'm going through those fast because I want you to go through them slower, but I wanted to point out those things before I did example 15. So in example 15, we want to consider three different functions here. F of x equals x times the sine of x, g of x equals x squared plus 2, h of x equals the absolute value of x. So those are actually three pretty common functions, and I would hope that you could recognize those as all be continuous everywhere. Right, x sine x, think of that as a function. We know sine of x is continuous everywhere. It looks like that wave. And x is just the straight line x, so multiplying the two of them, that's also a continuous function everywhere. X squared plus 2 is just an opening up parabola shifted up 2 units on the y-axis. That's continuous everywhere. The absolute value of x, you know, hopefully that looks like a v, right? V touching 0, that's continuous everywhere. So when I look at compositions of these functions, like for example, if I looked at h composed with f divided by g of x. So what does that mean? Well, composition of functions means that that's h of the quantity f divided by g of x. So we first have to do f divided by g. So this is f divided by g. Then we plug that in for x everywhere I see an x and h of x. And so I get x sine x over x squared plus 2, all absolute value. So that composition of functions is going to also be continuous everywhere. Since all three of those functions were continuous everywhere, the composition of them will be continuous everywhere. The only place you would have to worry about is if you were ever dividing by 0, but x squared plus 2 can never be 0, so you're never going to be dividing by 0. And that's an example of what this composition of functions looks like.